Hey Dragons, today's lesson is over exponential growth and decay, and this is an offshoot from our exponential work that we've been doing. Our general form is going to go in two directions, and it's all dependent upon the base. If the base is bigger than 1, you're growing, and if it's not, if it's less than 1, it's going to be decaying or getting smaller. So let's look over here at how the growth formula is going to change on us. The base will be written as something in this form, 1 plus a rate, a growth rate, and that's going to guarantee that the base is going to be 1. A is still my initial amount, and T usually replaces the variable x because we're usually going to be talking about time. So we're going to be talking about growth over time. Y is going to be the final amount. So we're going to start with this. The base is going to tell us how we grow. The exponent is going to tell us for how long. And then the y, the dependent variable, is going to be telling us what my final amount is going to be. So the base can also be called growth factor because factors imply multiplication, and repeated multiplication is the whole basis for exponential functions. See the multiplication right there? We use factor. Here's an example of a growth exponential. Notice that the base is more than 1. The starting amount is 700, and I have the time in years, and I have the final amount. And we're going to work some of those in just a second. Now, if we break this down, whatever is added to the 1 in order to make it greater than 1, in this case it's 0.05, that can be called the growth rate. And rates are usually written as percent. So if someone asks you, how much is this growing? We're going to say it's growing by 5% per year. Okay? A lot of people think that the growth factor and the growth rate are the same, and they're not. The factor is 1.05. That's what you're actually multiplying by each year. Okay? And this is the percentage that boosts you over the value of 1, and that's what makes it a growth. Okay, so let me show you an example of a decay. It's going to be very similar, and then we're going to do a couple of problems. Alright, so again we start off with our general exponential function. Decay's base is less than 1. I didn't write this in, but this is going to be 1, but I want it to be less than 1 in order to decay. So I'm going to subtract my decay rate. Alright, so this number right here, the base, again, just like with the growth, the base might be called a growth factor, and in a decay it's going to be called a decay factor. But everything else is the same. I still have a starting amount, I still have a time, and I still have a final amount. So if we focus here on the decay, here's an example. I start off with 68. And you notice that my base is 0.85, which is less than 1. So this thing's going to be going down. All right. So how do I write 0.85 using a 1 minus? Well, it's going to be 1 minus 0.15. 1 minus 0.15 is the same thing as 0.85. Now the reason why I do this is because this part that's not the 1 is going to be called your decay rate. So my decay rate is going to be 15%, and if you just look at this by itself, you don't see the number 15. Okay? You actually have to do this little math going back to this 1 minus format. Well, 85 cents. How do you get there? Well, you take $1 and you subtract 15 cents. So if you have a decay base, you're going to have to think like this in order to get a decay rate of 15. Alright, let's do some together. You have your handout and all what I just explained. You have it up here. tells you what it is. So here's problem number 1. Let's do this together. Go ahead and fill it in. And here we go. We got the population of a town is 18,000. Okay, 18,000. Does that tell me that's the initial amount right here? 18,000. So I'm going to come over here and squeeze in 18,000. Yeah, I know my blanks are a little small. Sorry about that. And is decreasing at a rate of 2% a year. Okay, so if we look over here, it says we're decreasing. That's pretty obvious right there. Decreasing is decay. So over here where it says to circle one of these, decreasing means that we're decaying. So we circle that. All right, so we need our growth factor. Actually, it's not a growth factor in this particular case, it's a decay factor. So let's scratch that out and put decay. Sorry about that, I didn't catch it. So it's a decay factor, and so what we're going to do is we're going to look over here and say, all right, well, what's 1 minus my rate? My rate is 2%. So I'm going to do 1 minus 2% written as a decimal. Remember how to change your percents to decimals? Divide by 100 or move the decimal 2 spaces to the left. So if I do that, I actually have 0.98 as my base. So now I have A, I have B, and if you remember back in the general formula, that's what we had right here. So my equation is going to be y equals 18,000 times 0.98, and we need our exponent, and since we're talking time over time, we're going to use t. My rate is 2%, and my domain, well, if we're talking about time, time is always going to be positive. Okay, and when we look at this, my range is talking about the population, and it's going down. So my range, my y value, needs to be, since it's going down, is going to be less than 18,000. And for all practical purposes, it's going to stay positive. Now, it's really probably not going to get very close to 0, but it could possibly go away if it becomes a ghost town or something like that. All right, so we have our equation. And so now we're going to come over here and actually plug it in. How long does this problem want us to consider this? And you look right here, it tells us to consider it for 6 years. So my time is going to be 6 years. So let's take this equation, grab our calculator, and plug in a 6 for t. And it's going to look like this right here. See if I can't get that to show you. All right. So we're just going to substitute 6 in for my time. Again, you can either do 0.98 or you can even just type it in as 1 minus your growth rate here and press enter. And we're going to round to the nearest whole number. So this is 15,945 people. Now, is that guaranteed? Of course not, but it's a good estimate. All right. So did it go down? Yeah, it started at 18,000 and now it's a little less than 16,000. It's an example of a decay. All right, so let's look in one more. And again, I apologize. This should either be growth or decay depending upon what you circle over here. So let's see what's going on in this problem. We got annual sales are 149,000, so that's my starting amount, and your starting amount, your initial amount, goes right here. Yeah, I'm going to have to squeeze it in, sorry. And increasing is growth, so we'll circle growth. We'll have a growth factor, so I don't need to scratch that out. Okay, and remember your growth factor back up here. You're going to add 1 to whatever the rate is. So the rate is 6%. So the growth factor is going to be 1 plus 0.06 or 1.06. So my equation is going to be y equals my starting amount, 149,000, times 1.06 raised to the t power. Should have checked these sizes of these blanks first. All right, and again, the domain, we're talking time. Time is going to be positive. Okay, and if we look at the range, it looks like we're starting at 149,000 and getting greater. So y can be greater than or equal to 149,000. Now, will it continue to get bigger, bigger into the quadrillion, zillions? Probably not, but for this particular example, we're just going to leave it at that. So we got the equation. How long do we want to check this graph? We want to check it for 7 years. So again, 7 years is my time. And so we'll come over here and do y equals 149,000 times 1.06. Again, your base is greater than 1, so it's growing, and we're going to put a 7 there. Grab your calculator, and makes it a lot easier. So 149,000 times 1.06 raised to the 7th power. 6, I typed a 9 for some reason. And about $224,040, 41 rounded out, whatever, close enough.